Welcome to the 105 Lab 10, Hubble's Law. You may have heard of Edwin Hubble before. He's an incredibly well-respected astronomer. He looked at galaxies and classified them as galaxies. He's the one who came up with different classifications for them. It's all sorts of cool stuff. A galaxy is a really big island of stars, and he's the one who determined that. The Hubble Space Telescope is named after him because it is continuing on his work. It's looking in far off places, finding galaxies, and sort of tracking them. Here we can see a lot of the time we measure the velocities by redshifts, and he measured distances to nearby galaxies using Cepheid variables. So that's kind of how you're getting your information, and he just graphed it. On the bottom, he has the distance, and on the side, he has velocity. This graph is actually really cool because it was a hand-drawn graph that Edwin Hubble had put in one of his reports. The dots are galaxies, the not filled in circles are clusters of galaxies that he just averaged the brightnesses together. They're like really close to each other. And the line of best fit there sort of helps you find how fast they're going in relation to how far away they are. And that's what we're going to be doing today. So here we can see that we have the Milky Way galaxy. We obviously can't move away from ourselves because we're inside of the Milky Way galaxy. So our velocity is 0, and our distance away from each other is also 0. You may notice back here on the graph that the line started at 0, 0. That's why the Milky Way galaxy goes there. So, if we go to the closest galaxy to us, it is moving away from us at 700 kilometers per second, and it's 10 megaparsecs away. Cool information on its own, but let's look at one that is twice as far away. It is now moving twice as fast away from us. Same on this side, it's twice as far, it's moving twice as fast. All galaxies are doing this. The further away they are from you, the faster they are moving away from you. And it's not just things moving away from us. We're not necessarily the center of the universe. Here, we see an alien's galaxy. We are moving away from it just as fast as it was moving away from us. So, because everything is moving away from each other, we can conclude that the universe is expanding. Now, I like to think of the raisin bread analogy. If you haven't heard of it, that's okay. So you have this dough with raisins in it, like bread dough. And when you cook the bread expands, right? And therefore the raisins move away from each other. But they stay in the same relative space as where they were. They didn't move in the bread. The entire loaf expanded. And that's a sort of similar thing with the galaxies in the universe. Alright, so here we have our Hubble diagram. We see distance in megaparsecs, recessional velocity in kilometers per second, and we always start at 0, 0 because the Milky Way galaxy is there. So here's Hubble's law. We have an equation of a straight line. This is the line of best fit when you plot a bunch of galaxies down, and it's pretty easy. In algebra you learn y equals mx plus b. So we have our y, our slope, our x, and our y-intercept. Well, if we start at 0, 0, our y-intercept has to be 0, right? So we can basically ignore that term. Then we just have to define the rest of them. Our y is recessional velocity, our x is distance, and our slope, rise over run, your slope, is what we call a Hubble's constant. Our Hubble's constant is really important to us, and we can actually figure out what it is pretty accurately. It has changed over the years, but the more information we get, the better Hubble's constant we can get. So, pretty cool stuff. From this, we just replace, y and x and m with what we know, and we get Hubble's law. So it's just equation of a straight line, basically. Now, if we are trying to find, say, a distance, you just rearrange your Hubble's law for the information you have. If you know your velocity and you know your Hubble's constant, or the slope of that line, you can figure out a distance. Another way to do this is graphically, right? So you measured the redshift of some galaxy, so you know the velocity of it, the recessional velocity. You can do it graphically. You come over here, you say, oh, it's 10,000 kilometers per second. You go to the line and you look down, relates to 132 megaparsecs, or you just plug those numbers in over your Hubble's constant and you get the same thing. This actually doesn't matter because it's online and you guys can write on whatever you want. Alright, and we will be supplying this image to you. Please make sure that you look at it when it's like 100% big so that it's not distorted in any way. But you're going to be using this handout here in order to find two things: the distance to these galaxies, and you're going to use the spectrums to find the recessional velocity, the redshift. So let's see how that works. First, we're going to measure distance. So, something is closer to you, it's going to look bigger, right? It's closer to you, the angle that you see it, it's twice as far away, you'll see that angle as half as big. Makes pretty good sense. We're going to be looking at these different galaxies. Now, I will mention that for these two, Virgo and Ursa Major, they look less circular. In reality, they are all about the same physical size, but Virgo and Ursa Major just happen to be close enough to us that we can see they don't exactly look circular. So when you take measurements, measure first long ways, then short ways, and then add them up and divide by 2, or average them together in order to get your actual answer. So these are elliptical galaxies that are about the same physical size, or 0.032 megaparsecs. All 5 of these are about the same physical size, right? Therefore, if we see it smaller, it has to be further away. Now, here's a bit of fancy stuff we're going to be working with. We see these angular measurements. So S is how long that galaxy is, which we already know is 0.032 megaparsecs. The theta is how big we see it, which you're going to measure, and the R, the radius, or the distance to that galaxy, is what you're finding. So we just rearrange this formula, and our distance, or our radius, just uses this formula. You're finding the theta, you're just going to measure how long that is, add them up, divide by 2. For Corona Borealis, Boötes, and Hydra, you can just straight up measure them because they're small enough they look pretty circular. But I will give you a hint that Hydra is 1.0 millimeters, and it is the smallest. And because of that, Boötes here has to be larger than 1.0 millimeters. Please measure to the nearest half of a millimeter and then convert to radians. It's all good stuff there. Just do not say Boötes is 1.0 millimeters or smaller, because it's not, and we'll count it wrong. Alright. Moving on to recessional velocity. So I already looked at the picture, now we're going to look at the spectra. We can see that right here and here, we see 2 different absorption lines. Remember, absorption, emission, and continuous spectra. It's all important. Went over a couple times ago. So, we're going to go to this second line, second absorption line here. That's what we will be measuring to. That's the goal. First, we do have to make a plate scale. So we know in nanometers what the wavelengths are from here to here, and now you can measure it in, I believe, millimeters, and find your plate scale, just like you did previously. And remember, you're going to that second absorption line. That's what you'll be measuring to. So from this first line, this first very bolded emission line, to the second absorption line, you have to measure all that distance. Now there are arrows that are on the spectras to help you see where the absorption lines are. Do not just measure the arrows. They are not all the way long enough. You do want to measure as precisely as you can from the emission line to the absorption line. So here we have a couple steps. You measure the distance and then convert it using your plate scale that should just have done. Our recession velocity uses this formula. So we're looking for velocity. We have c, which is the speed of light that's given to us. We have lambda naught, which is a lab wavelength, which is also given to us. And here we have lambda, which you are finding in millimeters. You put them all together and you get the velocity. So once you have the distances and recessional velocities, you're just going to plot all of your points. Plot your beautiful data points. Don't forget about the Milky Way galaxy. Remember, it makes your life very easy. Because once you plot your data, you have to make a line of best fit. Now, a line of best fit does not necessarily go through your points. It is a straight line that starts at 0, because at the Milky Way galaxy has to start at 0. And it tries to have the same amount of galaxies above as it does below. Alright, so try your best to make your line of best fit. If you have questions about that, you can take a picture and email it, and I can look over it, see if it looks like it'll be a good line of best fit. Because if it's not a good line, it really messes up your next calculations. So now you're going to find the slope, and the slope is your Hubble's constant. You can use rise over run to find your slope, but the easiest way to do this, I found, is you need 2 points in order to find your slope. The first one, choose a point on your line where it touches the corner of the graphing grid, and try to make it in the further part of your line. For whatever reason, the numbers just tend to work out better if you use the second half of the line over here. And your second point, make it 0, 0, so that you don't even have to worry about it. Alright? So rise over run, and try to choose a point in the second half of the line. Okay, so now, estimating the age of the universe. So we have a house and 2 cars, and these vehicles are going to go away from each other, opposite directions. We know how fast they were going and how far they went, and we want to know how long they've been driving, right? That's pretty easy. The time equals distance over velocity. It's an equation you should be familiar with. So we put our distance additive, so this one went 120 miles, this one went 120 miles, so together they get 240 miles, divided by the velocity. Again, you add them together and get 120 miles per hour. You put it in a calculator and you get 2 hours. Now, that may have been pretty easy math. You could maybe even do it in your head. But now we're going to do it with galaxies, because you can do the same exact thing with galaxies. With the Milky Way and some other galaxy. We know that at some point they were together at the same spot, and now we know how far away they are and how fast they're going, and we want to know when they were at the same spot. That's our t equals 0. So, remember Hubble's law? It'll make our life a little easier. We have time equals distance over velocity, right? Here, we're saying velocity equals our Hubble's constant times distance. So we plug that in for v. We can cancel out our distances, and we're left with time equals 1 over our h naught, or our Hubble's constant. That's why making sure that the slope of your line of best fit is good. It's really important because it can mess with your Hubble's constant, and then you might get the wrong age of the universe. So here's an example on how to do this last bit. It's really just a lot of unit conversions, right? So we know time is 1 over the Hubble's constant, and we can just plug our Hubble's constant in. This is an example one. Don't just use this Hubble's constant, use your Hubble's constant, okay? We just said 1 over Hubble's constant with some units. And those units are pretty confusing, so we're going to write them in a different way just to make it a little easier to see what's going on. Make sure when you're showing your work, when you're doing this, you do show all of your work. You do have to write all your units out because we need to see how they cancel out. Right, so the first conversion factor on your paper, here it is. It'll help us get rid of megaparsecs and kilometers. So we multiply them together. We get rid of our megaparsecs, we get rid of our kilometers. Remember, you multiply by anything on top and divide by anything on the bottom. You put it in a calculator and we're left with something 10 to the 17 seconds. So now we're in time for sure, right? We're in seconds, but that's a lot of seconds, and I don't know what that means. So now I'm going to convert it again, and this time we're going to go into years, because I know how long a year is. It's kind of easier to figure out. And it's pretty easy to figure out how many seconds are in a year. So we use our conversion factor, cancel out our seconds, now we have our answer in years. But 10 to the 10 years, that's a lot. I still don't know what that means. So we're going to convert it one last time into billions of years. We didn't show that conversion on here, but make sure you show your work. Do show us how you convert it into billions of years. And we get 16 billion years old. So that's the age of the universe. You just did something really awesome. Alright, so I know there's a lot of steps to this lab, but just take it one step at a time. It shouldn't be that difficult, but if you do have questions, please, please, please ask. I'm always willing to answer your questions. Please don't wait until the day before it's due, because I might not have time to get to your question. Alright. Have a great day.